So this next question goes back to the kind of the beginning of the chapter where we were conducting some experiments by measuring the height that some different varying rubber balls would bounce when dropped from a given start height. And we called that difference between the drop height, it's actually the ratio between the drop height and the height that it rebounded up to, the rebound ratio. And just for a simple, I mean, these numbers, they're not intentionally, difficult to deal with, but just a little bit more intuitive. For example, let's say that we dropped one of the balls at a height of 100 centimeters, and after one bounce, it came back up to 50 centimeters. Well, our rebound ratio we calculate by taking this value 50, right, the next one in the sequence, and dividing it by the one before it. So we get a rebound ratio here of 1/2. So as I move forward, right, multiply times 1/2. Move forward, multiply times 1/2, right? So this would be 25. And if I multiplied the 25 times 1/2, it'd be at 12.5. So, if this is the original drop height and this is what it rebounds to, your rebound ratio is 0.5. And every single time the ball is going to come back up 50% from where it was the time before. So for this example, or for this problem, right, the original drop height is 2,000 centimeters and it rebounds to 1,700. I'm going to do the exact same thing. I'm going to take the 1,700 and divide it by the initial drop height, 2,000. And when I do this, we get a rebound ratio. You can reduce this to 17 over 20, but this is exactly 85%, 0.85. So every single time that it bounces, it recovers 85% of its previous height, right? So you can imagine it's always diminishing, right? 0.85, 0.85, 0.85, 0.85. So this is our rebound ratio. And again, how do I get that? I get where it rebounded to divided by the original drop height. And don't get too carried away about it. Just think about, an example like 150. And if you start at 100 and it rebounds to 50, that rebound ratio is 0.5, 50%. So you should be able to figure out the arithmetic to do to calculate what the rebound ratio is. The next question says, find the rebound height after the second bounce. Well, we know after after the second bounce. Okay, so here's the original drop height. This is the first bounce, 1700. So the second bounce would be, you take the 1700 and we're going to get 85% of that. So I'm going to multiply this by 0.85. And when I do that, I get 1,445. I think these are centimeters, right? So after the second bounce, that's where it goes. Now, this original drop height, right? This is before any bounces. So this is zero bounce, right? That's just where we take it to release it. This is one bounce, and down here, this is two bounces. So it says find an equation that could represent the rebound heights. So for this, right, it's clearly because I keep multiplying by 0.85. This is a geometric sequence. So it involves repeated multiplication, and we show repeated multiplication with exponentiation. So this sequence should look something like this, right? The rebound height for any nth number of bounces is, we're starting out, our zero term is 2,000, that's worth no bounces, and then every single time it's 85% of the previous height, and then we just continue to multiply that by that 0.85 again and again. So if I want to know, for example, what it is after one bounce, well, n is 1. If I want to know what it is after two bounces, then n is the number 2. So boing, boing, and then that would give you that. So just repeatedly, it gives you the height that it comes back to after a particular number of bounces. Question D says, find the rebound height after the 10th bounce. So this is a problem that's made easier by the equation above, right? Because if I want to know what the 10th after the 10th bounce is, I'm just going to plug this value into this function. So it would look like this, right? It would be our initial height times 0.85, and we'll raise that to the 10th power. Let's grab our calculator and run that through there. So 2,000 times 0.85, and then I'm going to raise to the power of, and your calculator display will look a little bit different than that, but This little up arrow here is how you get up into the exponent, so raised to the power of 10. And when I do that, it says that after 10 bounces, it should rebound to about 393.7. So I'm just going to round that up to 394, about approximately 394. And these were, what were the units? Centimeters? Yes, 394 centimeters. And again, I think that, you're starting with integers, and realistically, based on the measurements we were doing in classes, I think even rounding to the nearest whole centimeter is probably a little generous. Okay, so that's the end for question 2.